It's time to start analyzing sine and cosine functions. And there's a lot to get in here, so I'm going to go as quickly as I can, but I need you to understand every little piece of this. So I want to make sure that you're getting all of it. I'm going to underline a couple of things. So the first thing I'm going to underline is we have these functions written in a certain way, and they're all going to be written like this. All right, and A, B, C, and D have different meanings. So A is amplitude. That's how tall your sine function is, or your cosine function is, for that matter. B helps us find the period, and I'll get to that soon. C helps us find a phase shift if there's any sort of movement to the right or to the left, and it's going to be, see how it's inside the parentheses. Remember, it moves us over to the right if it's negative, and moves us over to the left if it's positive. And D, this D out here is sort of our constant, is sort of, our y-intercept, but what it does is it moves our midpoint upward or downward depending on what D is. So let's start with what an actual sine or cosine function looks like. And the cool thing about sine and cosine is that they're waves, and they look very much the same. But I'm going to graph this, okay? And so I'm going to graph here, 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 and here on the x-axis, because the period of a sine function is 2 pi, and that's the amplitude, and its parent form is 1. It's the absolute value of 1. And so I'm going to do the same thing here. Graph up here, graph down here. And somewhat like this. So the sine function comes up, and it crosses through here, and it jumps down, and then it crosses back through the middle and up and over. And that was a little bit stretchy, wasn't it? And so it looks something like that. Cosine function is very much like that. The cosine function actually just is shifted over a little bit. So cosine starts up here, crosses down through here, right, and goes here, here, here. And I know it's taken me time to do this, but it's gonna be worth it just to see the difference between the two graphs. And so I'm just going to follow this line. I'm going to turn and come back up, and then swoop back down, and then come back up. And it looks something like that. And not a big deal, right? They're just shifted over a little bit. They both have an amplitude of 1. You see that the cosine function here, that's the green one, starts at 1 on the y-axis, right? 0, 1 on the y-axis, whereas the sine starts down here at the origin, okay? And so they both have an amplitude of 1, so that means that their range in their parent form is negative 1 to 1. Their domains are infinite in both directions. That's, they're both the same that way. And so we'll start moving on after this, and we're going to jump right into what amplitude is. And I'm going to go ahead, and now that you've seen this, I'm going to go ahead and get rid of this. Just give me one second to get rid of this. Actually, I don't want to do that. Let's not do that. Sorry while I work. Let's just do that. And let's go Let's see if I can get rid of all these dots. Sorry. So we saw that those functions look like that. If the amplitude is changed, you know, say it's y equals 2 sine x. Well, that just means that instead of going up 1, it's going up 2, you know. But it hasn't changed anything else, so it would still go up here, come back through here, get way down here, cross back up this way. Same idea, you know, way down there and come back here. So it's very much the same. So A is very simple to understand. If it happens to be a negative A, right, we know that the amplitude will be, you know, whatever the absolute value is. So if this were negative 2 sine x, oh, sorry, I forgot the x, then it would face the other direction. It would go this way. So, you know, I'll show you y equals negative 2 sine x. It would just go in the opposite direction. It would just go down and then come back up and then come down and then come back up and then come back down. All right, so that's what happens when you have a negative A. Not a big deal. Pretty easy to understand amplitude. The next part is a little bit silly, you know, a little bit more difficult when we're talking about, hey, what's going on here? And it's the period. All right, so if our sine function has a period of 1 or 2 pi, that means that's one whole period right there, going all the way to 2 pi. If we actually have a larger number here, let's see if I can erase here. Nope, not letting me erase. There we go. Let's get rid of it. I don't know why it's being all brushy like that, but there it is. Get back to that. If I had something that looked like, let me jump into another color here, y equals sine, let's say sine 2x. Let's make it nice and easy, okay? All that means is that instead of one whole wave in the 2 pi area, it would have 2 of them, right? It would double the number of waves we would have in that 2 pi area, that space from here to here. So we would have one full wave, and that's the whole up and the whole down, right? So it would have to go up and down and up and down and I don't know why it's doing that. Now I know why it's doing that, but sorry about that. Woo! There we go, we've connected it. So that's what happens when we multiply it. Now, if I multiply by a fraction, that means it gets really, really spread out. It would go much, much farther. You know, if I said sine x over 4, it means it would only make one whole sine wave way over at 8 pi. We'd be way off the chart over here. And so that's how that works. That's, you know, cosine works the same way. Wow, look at how beautiful this is. Okay, so if I'm talking about the cosine, and I'll just show you a picture of the cosine wave if we have y equals cos 2x. Cos 2x, right? And it would just start here, right? And it would make its full round all the way. I did it wrong, didn't I? Here we go. It would make its one full round here, and then come back up here, and then cut through the middle, and then cut back up here. And sorry about the wavy line there, but you'll get over it. All right, so that's period. Frequency is kind of cool. It tells us how often this thing repeats. Frequency is 1 over the time period, and that is a very, very popular idea in physics. So when you get to rotational motion and you talk about frequency, you talk about waves, and we talk about frequency and time period, knowing that the frequency of a wave, and that's what these things are, by the way, these continuous waves, 1 over the time period is a very, very important thing. So when we talk about the frequency of a wave, we would, take our 2x, right? And we'd say that it would be 2 over the period. Well, we found the period to be earlier to be pi, right? Because if our b is 2, right, we have 2 pi over 2, which meant our one whole wave would be right here at pi. So our frequency is 2 over pi. And all that tells me is that, I have 2 waves in here. The next thing we talk about in this is phase shift. And this is kind of a cool idea, this phase shift thing. Let's go ahead and pull this back. We'll get right back to these parent functions. We love parent functions. I know you guys love parent functions because everybody does. But let's go ahead and just use these easy functions, and I'll try with y equals, I don't know, sine x, sine x minus pi, right? It'll be in terms of pi, right? And really what that says is it's shifted halfway, right? So sine x is remember, was this guy, right? I'm just trying to do a little dotted line here and down to the bottom and then right there. So that's the sine x piece, right? But I'm going to shift it over. And so c, which is pi, over b, which is 1, is just pi. So I'm shifted over one whole space. And because it's negative, we shift over to the right. And so this would look like this, because it would start and it would continue on, of course. Because it's been shifted over. This is actually the start of the wave, and this is actually the completion of the wave. It's been shifted over 1 pi to the right. And that's really the simplest way to look at this. Now, our problem is if we have a period, that's shrinking our wavelength, then we have to worry about, this phase shift being shifted over a little bit more. And we can do some examples later on, but I want to give you the ideas first and then move on to actually taking care of problems from our text. I'm going to leave that there. Nah, I'm going to get rid of it. So the last thing we need to talk about is that vertical shift. And it's really a simple idea. It's a vertical shift. And I'm going to use this. I'm going to just copy over. I'm going to make this 2. And put a 1 in here. And all this says is that if I say it's, y equals cos x plus 2, that just means that my midpoint of the wave has been shifted up 2 spaces. So really and truly, instead of starting at 1, I'd be starting up at 3. So let's extend this a little bit and go to 3. And I would start my wave here, but I'd still have I do that. Now this is not quite what we want to look at, right? So we'd 3, okay. So we'd start here, and there we go. That's more like it. It is a big long wave like that. And that's what it would look like. It's just shifted up. So my midpoint, which is, this part across here, is shifted up 2 spaces. And really, that's all there is to it. There's some work that you have to do in terms of using these values to understand how to do some of the problems on the homework. So the next video that I do is going to take a couple of homework problems and show them to you. But for now you know what amplitude is. That's how tall the wave is. We went through period, and that's just dividing by whatever this wonderful coefficient is, and frequency is 1 over period, phase shift, and vertical shift, which just gives us our midline on the y-axis. That's it. Thanks for listening. Another video coming up shortly.